Okay, so over the last couple of topics, we've been discussing electromagnetic radiation, very specifically the idea of is light a wave or a particle? And the answer to that question is yes. It's both, right? And we have some evidence of both. I kind of give you that on the opening paragraph here. They had evidence that light was a wave, but they also had evidence that light was a particle. And then Einstein made a prediction. Well, it wasn't Einstein, but physicists made a prediction. They figured that photons, because they act like particles, they should exhibit behavior similar to particles. Matter has the property of momentum. If it's matter, it can have a mass, it can have a velocity. And they figured, well, why can't a photon have momentum as well? That was a prediction that they made, basically. And so they put together two different formulas. And here are the formulas. They're on your formula sheet here. P equals h over wavelength, or hf over the c value. And they made a prediction that these would be true. Okay. But I wrote down here, the hard part was proving it. How do you prove the momentum of a wave, right? Because a wave really isn't matter, it's light, it's X-rays, it's, you know what I'm saying here? So here, by the way, it was their proof as to how they came up with these formulas. So here is where the formulas came from, so that you can follow this logic. Momentum is mass times velocity. Okay. Now, we haven't used this formula yet, but we will in our final unit. You guys have seen the formula E equals mc squared at some point in your life. It's Einstein's famous mass energy equivalency formula. So assume that we will learn this formula eventually. They took this formula, rearranged it for mass, and got energy over the speed of light squared. And they took this, and they plugged it in there, giving you momentum is E over c squared v. However, v's velocity, but isn't c, oh, I guess you guys don't know this yet. C in this formula here is the speed of light. And isn't the speed of light of velocity? So because of that, really, these two things are the same as each other. So they canceled this velocity with that velocity and got to here, P equals E over C. But hang on, this is a wave, and Planck had already proved that a wave is h times f or hc over wavelength. So they either put hf in the spot of E, or they put, they rearranged it and did h over wavelength. Those are like the two formulas they came up with. Okay. So the long story short is that they actually did this algebraic proof first, and they said, I predict that momentum is possible via waves. But they had no way to prove it experimentally until 1923, A.H. Compton came up with an experiment. Here's basically the idea. He shot some waves at graphite particles, like a graphite sheet, very similar to the, you guys know the Rutherford experiment, how he shot particles at gold foil? Only he wasn't shooting particles here, he was shooting a wavelength. Okay? And here's what he expected. He expected you to shoot a wavelength in, it would then hit the particles here, and it would compress. That kind of makes sense if light is a particle. Or even if light is a wave, really, right? Like, if light comes in with a long wavelength that hits this, and it comes through shorter. This is not what happened. What actually happened was this. Wavelengths came in, it hit this thing right here, and it kicked out an electron. Now, we've already discussed this before, right? Isn't this essentially the photoelectric effect? Energy comes in, my bowling alley analogy, fellas, please. The electron gets booted out, but here's what he discovered. There was actually a wave emitted in the other direction, and this wave emitted in the other direction was actually a longer wavelength. Let's talk about this for a bit. This short wavelength, this one's shorter. If it has a short wavelength, it means it has a high frequency, which means it has a high energy. That make sense? Well, some of that energy is now in the form of 1/2 mv squared. And some of it maybe is lost due to like the work function, but really the rest of it, there was actually some wavelength left over. And this now has low energy. Why does it have lower energy? Because it has a lower frequency, because it has a higher wavelength. And so using conservation of like energy and momentum, this kind of makes sense. You have a lot of energy starting here. Some of the energy got converted to booting the electron out, but some of the wave didn't just stop. The wave actually like refracted at an angle. Okay? And so using both conservation of energy and conservation of momentum, Compton basically put together a new formula. He named it after himself, because that's what scientists do, and he called it the Compton Effect. Okay? And this was actually a breakthrough. Did I have that word here? Breakthrough? Yeah, here it was. It was a breakthrough for basically scientists finally deciding that the answer to the question, is light a wave or a particle? The answer is yes, both. You know, they finally seem to have definitive proof that it's both a particle and a wave somehow. Okay, so here's how this works in another picture. You have gamma rays coming in with high energy. The gamma ray hits something, boots the electron out this way right here, but rather than stopping, like in the photoelectric effect, when I've already shown you one before, I've shown you a particle coming in, the particle comes in, hits this metal, kicks out an electron, and it's stopped. Now what I'm saying is this wave comes, hits the electron bounces one way, but the wave keeps going. But can you guys even see in this picture that how tight this frequency is right here? You see how this one's a little bit wider? Why is it wider? Because it's lost some energy. Where did the energy go? To the electron. So that's what we're going to do. Okay, I've already mentioned before that there are 3 places in the Physics 30 curriculum where you need to be able to do a 2-dimensional vector momentum-y kind of problem. Okay. One of them is momentum. One is when you do the exact same thing in forces and fields. This is the 3rd one. I don't know where they're going to give you the x, y. You know how you have to break it up into x, break it up into y, add and subtract them, do all that stuff? That's basically what we're doing today. Okay, just a new context. So anyways, let's get to some more of the concepts here. He shot in a photon. The electron went one way, the photon went the other way. And here's how we can calculate these momentums. Okay, anytime you're calculating an electron, which would be like this one right here, you have to use P equals mv because it's matter. Okay, so you're going to use its mass and its velocity. Where will you find its mass? Well, it's an electron. The mass of the electron is 9.11 e minus 31. Either you're going to be given the velocity or you'll be solving for the velocity. However, whenever you're solving for the momentum of either the incoming ray or the slightly longer ray that leaves, you're going to be using the new formula here, P equals h over wavelength. Finally, if you ever need an angle, this is known as Compton's equation. Okay? You're probably using this in conjunction with momentum principles. So this is Compton's equation. I believe it's on your data table. It's a little convoluted. Like there's a lot of parts to it. So let me walk you through it. It is on your data table, right? Top right-hand corner? Yeah, this is in the top right-hand corner. Okay, this is Compton's equation. If you want to find the change in the wavelength, by that I mean you used to have a wavelength that came in with this much energy. It then kicked an electron out this way, and the wave is now a wider wave. The wider wave means less energy, right? So if you want to find the change in wavelength from 1 to 2, you need to know Planck's constant, which we always know. Mass, well, what's the mass of an electron? C, the speed of light. And then the cosine theta is the scattered X-ray angle. By that I mean that the angle of the X-ray, however much it deviates as an angle, that's what angle goes in here. It's not the full angle between the electron and the wave. It's like as though it was going straight. It's this angle right here. So let's try an example. I literally just have one example for you. I can make more if you want, but hopefully what you're starting to see here is that it's the diagnosing what they're asking for in a question. That's the hard part. Hopefully doing the math of this, you'll be okay with that. But if you want more math practice, I'll find you more. So let's try an example. Let's say you have an X-ray with a wavelength of 10 to the minus 12 meters, and you shoot it at graphite, and it scatters at 15 degrees. First, I'm going to draw a picture. I'm going to draw a nice tight wavelength for an X-ray. It's then going to hit an electron, and the electron, I'm going to have it bounce that way. I don't really care which way the electron bounces, but let's assume it goes that way. If I were to have kept going on like a straight path, this new wave, which is now a longer wave, because it's now lost some energy, the angle that it's been deflected at is 15 degrees. Does that make sense for our setup here? Question 1, what's the wavelength of the scattered X-ray? So this guy right here is 1.28 E minus 12. We need to know what this wavelength here is. Literally all you do is you plug it into that Compton formula. It's actually pretty straightforward. So the formula was the change in wavelength was equal to, where was it again? H over MC times by 1 minus cosine of theta. Okay, let's plug in some numbers. H, 6.63 times 10 to the minus 34 is the H value in joules and meters, and like the normal one. We don't want the electron volt one. M for mass, 911 times 10 to the minus 31, because that's the mass of an electron. C is the speed of light, so 3 times 10 to the 8. Times that by 1 minus the cosine of 15 degrees. So hopefully this is okay to do, like the math part of it. It's the interpretation we got to practice. Here's what I got. I got 8.266, etc. E minus 14. Good. You got that too. You get that as well? Okay. So I'll give you guys a second to try that in your calculator if you want. But hopefully that's fairly straightforward. You're literally just plugging numbers into a formula. Okay. Now the interpretation part. What did we even find? We have now found a change in wavelength. This, most important thing, this is not the new wavelength. This is not the new wavelength. This is how much the wavelength has increased by. Say that one more time. This is not the new wavelength over here. It can't be. See how this is a wavelength to the minus 12? I now have a number to the minus 14. Minus 14 is a smaller number. It means that we would have now made an even more high energy wave than we began with. Right? We now need to take this number right here and add it to this number right here. So I'm going to add on, what was it, 1.28 E minus 12. And I've now got this number here. I got 1.36 E minus 12. Okay, I put a little rule on here talking about rules for sig digs for adding. I think it's worth it to take a brief second to talk about how I got to this, because some kids might suggest, Chris, there's only 2 sig digs here. This has 2 sig digs, Chris. Why the heck do you have 3 sig digs here? This is actually correct, the 1.36. Okay. Let me show why. Okay. I need a new slide maybe to do it, though. One of the numbers was 1.28 E minus 12. 1.28 E minus 12. And the other number was 8.266 E minus 14. 8.266 E minus 14. If I were to actually write out these numbers, it's going to take a while for me to do, so bear with me, but I'm actually going to write these numbers out like this. 0.12345 guys, please. 6, 7, 8, 9, 10, 11, there. So that's my first number. Does that work? And then the number that I'm adding to it is 0.12345 6, 7, 8, 9, 10, 11, 12, 13, 14, You guys see how that worked there when I wrote them out? So this one has 2 extra zeros on top of this one. When you are adding numbers in SIGDIGs, there's a slightly different set of rules. We rarely ever have to use it, but the rule is you cut it off with the least precision. And so the precision gets cut off right here. And so effectively what you have to do is take 128 and add 8 more to it. I know we have digits over here, but these digits don't really get to count at all. And so when I'm finished, this number now becomes 136, and then it's still to the minus 12. So it still appears to have 3 SIGDIGs, but there's like a funky rule for how this works. Because you're adding this number here, but there's extra zeros in front, you're really only adding like the first digit to the last digit. Okay, so if that doesn't make sense, maybe I can explain it more later, but the long story short is that this right here with 2 SIGDIGs does not affect this guy right here with 3. So we still have 3 SIGDIGs. So, yeah. If this one was negative 14, this one down here, 15, it might actually not affect it at all. It's actually possible that the wave scattering that you do right here isn't even enough to notice, if that makes sense. Like hypothetically, if this was to the minus 15, then what would have happened is you'd have had an extra 0 sitting right here, and then you'd have had the 280, and when you did this and you added this, literally nothing would have changed significant digits-wise. That is possible. Pretty rare, but yeah, that could occur. Okay, so let's try now the harder part of this question. Now we're going to try to find the velocity of the electron. So I'm going to redraw my photo real quick here. So we came in with a wavelength that looked like this. Okay. If it kept going straight, it would have gone on this line here. The electron went this way. My wave went down this way at 15 degrees. And I now know the wavelengths of both of them. But I don't care about the wavelengths. I care about the momentums. So I'm going to calculate over here px, the momentum of my incoming photon. And the formula that we learned a while back here is, where is it? P equals h over wavelength. So to find the momentum right here, it'll be h divided by wavelength. So that's going to be 6.63 times 10 to the minus 34 divided by my incoming wavelength, which was 1.28 e minus 12. And just like we did in so many of our momentum questions, I'm going to need to store these somewhere in your calculator. Like you need to organize this well so you don't make a mistake on this question. So I'm going to store that as letter A. You can store it as whatever letter you want. But so anyway, 6.63, 10 to the minus 34. I'll divide by 1.28, 10 to the minus 12. I am going to store in my calculator letter A as 5.17, etc. E minus 22. And so that is going to be my incoming x momentum. Then over here on this angle, I can do the exact same thing, only I have a different wavelength. So this is going to be P, why don't I call it PH maybe, like the hypotenuse? I don't care what you call it, but just make sure you know this is the hypotenuse amount. And it's going to be 6.63, 10 to the minus 34, divided by the wavelength here, which I think we said was 1.36 E minus 12. And if you can, though, use that exact number. Don't use the rounded number, use the exact number. So 6.63 E minus 34 divides by this number here. I calculated this hypotenuse momentum to be 4.865, etc. E minus 22. But I want to make a note that is on the hypotenuse. And why don't I call that letter B, just so that I keep things clear. So that's now being stored as letter B. Is everybody okay so far? So this one and this one, I use the new formula to solve for momentums in. Whenever I solve the electron, though, I'm going to use the formula P equals mv. But I'm not quite even to that spot yet. I'm not even that far yet. What I now need to do is break this triangle up into its x and into its y momentums. The good news is, like, you guys are going to be getting better at doing the momentum section. Can you see why I threw it first? Because, like, you might not have done great at it the first time, but you're probably getting better at finding the y and x components to this. If I want to find the x component, I'm going to take letter B, and I'm going to times it by the sine, nope, not sine, cosine of 15. And if I want to find this y component, I'm going to take letter B, and I'm going to times it by the sine of 15. Because this is the hypotenuse. So hypotenuse and opposite is sine, and hypotenuse and adjacent is cosine. So whatever this number is right here, I'm going to calculate x and y right here. So again, you need to organize this however you can keep track of it well. So b times cosine 15. B times cosine 15. I got this value here, 4.699 e minus 22, and I'm going to call that letter C, I guess. Store as C. And why don't I call this one letter D, the y direction one? So if I do b times sine of 15, I got this, 1.25 and change minus 22. So let me pause there for a sec, just make sure everybody who's trying this gets the same numbers as me. So I've got a 4699 number and a 1.25 number. Yeah, so I took this wavelength right here as the hypotenuse, and I'm finding x and y for it. Well, the wavelength has momentum is what we're saying now, right? So this wavelength right here, I found its momentum as this value right here on the hypotenuse, and I broke it up into x and y. Our momentums, this is a momentum in the y direction for the wavelength. And this guy up here is the momentum in the x direction for my wavelength. And then this one right here, if I want to write it, this is the momentum in the x direction for my wavelength. But when I eventually solve for this right here, I won't be using this formula here, the h over wavelength formula. I'll be using m times v when I eventually do this bit right here. So we got to get there next. Everybody who did calculations along with me, did you get what I got? Okay. Okay, so the last part here. I kind of need a new slide because I don't have enough room on one slide to do this. So give me a sec while I kind of redraw this. We had a momentum going this way, one going this way, one going this way, but it really got broke up into pieces. So if I can kind of like draw some arrows here, I believe this was letter A, this was letter B, this was C, and this was D. I need to now solve for E, F, and ultimately G. I don't care how you letter this or keep track of it, but like somehow we've got to like keep track of all these vectors here. So I've already found A, B, C, and D. I need to now use the electron triangle up here, E, F, and G. So how do I solve for E? What would the equation be to solve for this side right here? What two numbers do I need to solve for it? What direction is it going in? X or Y? Okay, so what other letters are X direction values? A and C. What should I do with A and C? Add them, subtract them? Subtract. And which order? A minus C. Because you had this much incoming energy, and now some of it's going to be transferred or lost, right? So some of it went to C, some of it went to E. Okay. So using your calculator, you should hopefully be able to calculate E by taking A and C and subtracting them. So A minus C gave me 4.799 E minus 23, and I'll store that as E. How do I figure out, so now I know E. How do I figure out F? Well, F is in the Y direction, right? What other Y direction numbers do we have? Just D. These two things will be exactly equivalent to each other. So really, D is F. However far this one goes down is the same amount that this one goes up. We're almost done then. How do I solve for G? Pythagoras' theorem. Okay. So if I take E squared, add it to F squared, and square root it, I will then have G. But I don't actually have F in my calculator because F is D. So I'm actually going to do E squared plus D squared in my calculator. So E squared plus D squared square rooted. I got this answer here for G. So I'll finally write it up here. I've got G as 592, basically. That's what I got for G. Anybody else get 592? Or did I screw up? Nope, maybe I screwed up. You have something different than that? Okay, so it's me then. Give me a sec here. Oh, I didn't save an answer as D. Shoot, why didn't I save an answer as D? Where's D in here? Okay, what is D supposed to be? D was supposed to be this number here. Ah, I'm glad I saved this here. So this is supposed to be stored as D. Okay, so clearly not 592. Let me try this again. How about 1.34 minus 22? 1.34? Okay, good. Okay, so that's on me, sorry. So I calculated a momentum up here actually of 1.34 times 10 to the minus 22, and I'm storing that as G. Okay, last thing though, it wanted the velocity of the electron. What have I solved for right here? What are all these units in? Momentum. So this is a momentum value. Momentum is equal to mass times velocity. So all we need to do to get its velocity is divide by mass. What mass do we divide by? An electron, because that's what this item right here is. So take this number and divide. I'm kind of getting a little messy here, I'm sorry. But like take 1.34 E minus 22 and divide, oh that's really bad, I'm so sorry. And divide by 9.11 E minus 31. And you'll have your velocity. And we're done. So divide by 911 E minus 31. I've got a velocity, and it actually kind of makes sense. I got 147,931,554. 1, 2, 3, 4, 5, 6, 7, 8. 1.47 times 10 to the 8 meters per second. Oh, you're right. Yeah, that's an 8, isn't it? Thank you. Okay, a couple of thoughts here. I wasn't actually focusing on the rounding. I was worried about one thing. If this number was bigger than 3 times 10 to the 8, we have a problem. You guys hear that? Because it shouldn't go faster than the speed of light. Okay. However, it kind of makes sense because this is an X-ray coming in with a huge, huge amount of energy, and it strikes a single electron. That electron is going to go flying, right? And so it's going pretty fast. That actually makes sense in context. If this number was like 7.48 times 10 to the 8th, though, that's too big. It couldn't be that big. So I do feel like this is a good sign here. Okay. One last thing, you could be asked to find this angle right here as well. If you were asked to find this angle, though, it's a pretty easy calculation. You just inverse tan the opposite over the adjacent, and that'll get you the angle if you're being asked for it. So I guess we could solve it real quick if you really want to. Inverse tan the opposite over the adjacent. What's the adjacent E? I got 69 degrees right here. Okay, that's my example. Because it takes so long, I only have one. If you guys want more practice on this, I can find you more examples of this, but more importantly, guys, I'm almost done. I'm going to let you have some free time in a bit here. The skills I need you guys to work on are probably not the typing numbers into formula skills. Probably not. If you need help with that, I can help with that. You need practice at interpreting, deciphering, and basically figuring out what the heck they're asking you to do in a question. Because they give you those really intense, big, like, pictures, and you've got to try to figure out, like, where do I get numbers from, and what formulas do I even use? Because there's like 80 formulas on this formula sheet, and you got to try to decipher which ones you're supposed to be using, right? So here's what I want you guys to do now. Let's ignore Compton for a little while, because my guess is that if you understand momentum principles, this is basically the same thing as momentum with one extra twist. All you have to be able to do is use these new formulas. And really, you just take Planck's constant, divide by a wavelength. That's not the hard part, okay? So can you guys work on a few things for today and tomorrow? Number one, try to do your first quiz, okay? It's hard, but I want to show you what sort of questions are on the diploma, because I want you to know what we have to work towards, what our long-term goal is. If you need me to help you every step along the way, I will. I want you to eventually get to the point where you're not asking me for help, right? But that's your call, okay? Are you the kind of kid when you're skating that you're using the little holding thing there? Are you getting my help the whole time? Or are you trying it by yourself, okay? This doesn't have to count. I don't even want it to count, okay? 2, you need to do some drills. So try the assignments, try the lab activities, and hopefully that'll help you build some skills as well. If you need help, again, ask, okay? My goal now is to take a bit of a break. This is hard stuff. Next week, we're not going to do any new lessons. We're going to spend a week doing a research project to kind of shift our mindset for a little while, let it sink in for a bit. Okay. I'm going to show you guys on Monday some examples of how this looks, but that's our plan next week. We're going to re-pick up the stuff then the week after that, and we're going to write 2 more practice quizzes before we finally get to a unit test. Okay. So if you don't have it down now, that's okay. We'll get there. Does that make sense what I'm asking you guys to do? And maybe more importantly, do you get my why? Like when Kevin and Mike and all these guys, they preach the know your why stuff, do you get what I'm trying to accomplish and why I'm trying to do it? Okay. Okay, so you have, I don't know, a little bit of time left today. You guys can scatter if you want, but please start doing some of those practice questions on the assignments and the lab. Okay, let me stop this and I'll answer your questions. That was 33 minutes. That wasn't bad. I said 40.